First speaker, yeah. Okay, shall we start the morning session? This session is gravitational wave session. Now the first speaker is Dr. Tae Hyun Jung from Florida State University. Talk title is Primordial Black Holes from First Order Phase Transitions.
Okay, thank you for the introduction. First of all, I would like to thank Professor Hyun Lee and organizers for inviting me this nice workshop. In this talk, I'm gonna briefly overview various scenarios of primordial black hole formations from first order phase transitions. And in the second half of my talk, I will go through the details on a specific scenario where bubble collisions produce primordial black holes. So let me start with a brief introduction to the cosmological first order phase transitions. So here is a scalar field and its potential that breaks symmetry spontaneously at 0 temperature. At the high temperature in the early universe, the symmetry will be restored, so the potential will be minimized at the symmetry restoring field value. As temperature drops, the potential shape will be closer to the 0 temperature potential shape. So at some point, symmetry breaking potential minimum should be developed. At this time, phase transition can occur, but if there exists a barrier between the symmetry restoring minimum and the symmetry breaking minimum, then the phase transition is first order. So the first order phase transition is driven by bubble nucleation and their expansion. So let me briefly explain what is happening. So here I depict the free energy in the space of field configuration. So metastable region refers to the field configurations living around the metastable minimum. Here, stable region refers to those field configurations living around here. So in order to make a transition from the metastable region to the stable region, you need to pay some amount of free energy. As depicted here, there is a transition surface. So you should overcome this here of the free energy. So the critical bubble is a field configuration on the transition surface that has the least amount of the free energy. So if I depict the critical bubble like here x-axis is the spatial coordinate. If your fluctuation exceeds this critical bubble, then it can fall down to the true minimum and the field configuration will expand. We call this expanding profile a bubble. So let me go a little bit further. So at high temperature, because the symmetry was restored, the space-time is filled by the symmetry restoring phase. Then as the temperature drops below the critical temperature, bubbles start to be nucleated, like here, randomly in the space. Then they expand and other new bubbles are nucleated. And in the end, they will collide. When they collide, gravitational waves can be produced. And those gravitational waves freely stream until today. So some of the models can be tested at future gravitational wave detectors like LISA or DESIGO and so on. But in my talk, I will focus on another outcome of first order phase transitions, which is black hole. So if black holes can be formed, then we can increase our testability, of course, because PBHs are detectable in various channels. So here I will overview several scenarios of PBHs. Here I categorize into two. First, localization of first vacuum region. Second, bubble collision. So let me overview the first scenario now. So the idea was first proposed by many years ago by Sato, Sasaki, Kodama, and Maeda. They considered a first vacuum region surrounded by true vacuum bubbles. Here C doesn't matter, so you can ignore this C part. Then what matters is the size of A. So if the size of A is large, then you cannot ignore the space-time expansion inside A because you have a larger cosmological constant. So this becomes like a Schwarzschild wormhole as this picture. If the size of A is small, then we can ignore the space-time expansion inside A. So the domain wall will shrink. At the same time, kinetic energy of the domain wall will increase. So if the total kinetic energy becomes larger than the size of A, then it becomes a black hole. So both cases, a black hole can be formed. Then these papers considered a similar setup, but in this time, they also considered some plasma is trapped inside the first vacuum region. So if some kind of plasma is trapped here, then as this region shrinks, the plasma becomes denser and hotter, so it can gravitationally collapse as depicted in this figure. I believe this was discussed in the yesterday's Joachim Kopp's talk, so I will not go through details. But anyway, in these works, they considered those surrounded first vacuum region from a random true bubble nucleations. So randomly happen to be bubbles are nucleated here, 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 and there, such that this region can be surrounded by those true vacuum bubbles. So therefore, the estimation of such primordial black holes relies on the probability of having such a surrounded region, but the probability is very difficult to be estimated. On the other hand, these guys, Kuzenko et al., considered a calculable model. So in this work, they didn't consider the phase transition, but the black hole formation mechanism is quite similar. So I will briefly mention about what is happening in their scenario. So they considered an inflation driven by two scalar field, and their potential is given like this figure. Along the radial mode, there are two local minimum, and this potential is slightly tilted. So the inflaton rolls down from around the top of this local minimum along this axial trajectory. So in the beginning of the inflation, you have a non-zero bubble nucleation rate because potential energy here is slightly less than the potential energy of the inflaton. So somehow bubbles are nucleated and they will expand until inflaton passes this line. So this line is determined by taking the potential energy of the inflaton to be equal to the potential energy here. Once it passes, then you can treat the bubble that has the field value of here as a first vacuum region as the previous discussion. Then it can become a black hole in the end. So anyway, let me move on. There was also another idea from these guys, Klopov, Konoplich, Rubin, and Sakharov. They considered bubble collision can create some first vacuum region, and such a first vacuum region can become a black hole. However, this idea was revisited recently by Lewicki and Vasconen, and here they simulated numerically a collision of two bubbles, and they found that first vacuum region can be created. However, the shape of such a first vacuum region is too flat to form a black hole. So anyway, there are many other scenarios as well, but I don't have enough time to overview every papers, so I apologize if I missed your work. Let me move on to the second scenario, where black holes are formed directly from the bubble collisions. So if the collision energy is large enough, then it can become a black hole, as the Hooke conjecture. So this idea was first proposed by Hawking, Morse, and Stewart in many years ago. But here they considered bubble radius to be much smaller than Hubble radius, such that they can treat the space-time as flat. In that case, they concluded that a collision of a large number of bubbles is required. So just two bubbles cannot produce a black hole if the radius is much smaller than Hubble. Followingly, Morse wrote another paper in 1994, where he released this restriction. He considered arbitrary size of the bubble radius, but instead he assumed the energy density profile around the bubble world is infinitesimally thin. In this case, he found that a collision of two bubbles cannot produce a black hole. However, in my recent work done with Takemichi Okui last year, we found that if I release this assumption, that means I take into account a finite size of the thickness of the energy density profile around the world, then we found that a collision of two bubbles can produce a black hole. So this will be my main subject. So you may wonder how to realize such a finite thickness of the energy density around the world. So let me give you a picture. So here is a bubble. Inside bubble, you have a true vacuum minimum. I mean, the scalar field is sitting on the true minimum, and outside the bubble, scalar field is sitting on the first vacuum. Then the thickness of this wall can be determined by some microscopic scale, like the mass of scalar field or wave of scalar field, whatever microscopic scale. And at the same time, you have a suppression factor coming from the Lorentz contraction. So gamma W is the boost factor of the wall velocity. This should be much smaller than the Hubble radius, because the Hubble radius has an enhancement factor from the Planck scale. However, this is not the whole story, because we have plasma in the space. So when the bubble world expands, there exists some frictional force coming from the plasma that is proportional to the gamma factor of the wall velocity. So this can restrict the wall velocity at some point. So there are two cases. If this power is larger than 0, then wall velocity is frozen by the value that equilibrates the potential energy difference and the frictional force. So in this case, this bubble world will work on the plasma. So the potential energy difference will be transferred to the fluid bulk energy. So bulk motion is generated along the bubble expansion. So you can obtain the profile of bulk motion by solving the fluid equation. And many people studied this topic and found that there can be 3 types of solution in the bubble expansion scenario. But the details doesn't matter. What matters is that the thickness of the profile. So in this case, the thickness of the profile is proportionally increasing as r. So the thickness can be quite sizable as the radius. I mean, here I will take this factor numerically around 10 to minus 3, so you don't have to worry about the next order of L of R. On the other hand, if the frictional force asymptotes to a maximum value, and if the maximum value cannot exceed the potential energy difference, then bubble wall runs away. So in this case, potential energy difference will be transferred to the scalar profile. So the kinetic energy of the scalar profile will increase. So the velocity will increase infinitely. So the bubble, so the thickness will decrease as 1 of r. So there is no possibility to form a black hole in this case. So please keep in mind of the first case as our picture. So from now on, I will go a little bit details of on what we did in this paper. Here is a brief summary of our findings. I will go through everything. So we found a condition to form a black hole, and then we estimate the number density based on this condition, and also we estimate mass based on this condition. So let me explain how we obtain the condition for the PBH formation first. So let us consider a bubble, single bubble, and outside the bubble, T mu nu is roughly given by delta V times G mu nu, because I'm considering supercooled phase. So I can ignore the plasma energy density. And inside the bubble, T mu nu is almost 0 because the potential energy is transferred to the fluid shell. T mu nu on the fluid shell will be quite large because all those energies concentrated on the fluid shell. However, the energy density and the energy flux are in the same order. So if I estimate the mass density will be microscopic scale. So if you have just one single bubble, then there is no mass generated. So let us consider another bubble, and let's consider they are colliding. On the collision region, flux will be cancelled because they are in the opposite direction. So the mass density can be large as the energy density. So we estimate the mass of this region by the integral of the volume of the energy density from each bubble times 2 because there are 2 bubbles. We factorize this formula into the angular part, and so we factorize this mass as the total energy accumulated on the shell times the angular ratio. So delta omega is the solid angle corresponding to this collision region. So now we can estimate. Let's consider the simplest case first. if the radius is much less than the Hubble radius, then we can treat the space-time flat. So the energy will be conserved. So the total energy stored in the fluid shell will be just the volume of the bubble times delta V. Therefore, if I plug this in, then I can estimate the black hole formation criterion. So black hole forms if the Schwarzschild radius corresponding to this mass becomes larger than the size of this region. Then you can find that the radius should be larger than Hubble radius divided by L over R to the 1/4. But this conclusion contradicts to the assumption that I started from. So, so we need to carefully consider space-time curvature to make the radius of the order of Hubble radius. So after some massive calculations, I'm not going through the calculations, but what you obtain is quite simple. From this massive calculation, or we obtain can be summarized by this simple redshift factor 1/2HR. So when I take into account the curvature effect, then the total energy accumulated on the shell is redshifted by a factor of 1/HR. So let me modify the previous estimation. So if I consider radius much smaller than Hubble radius, then I have a redshift factor of 1/HR. So here the power becomes 1 from 2. So here the denominator becomes L over R to the square root L over R instead of L over R to the 1/4. If I use this condition back into the mass, then I can obtain the lower bound of PBH mass, which is the Hubble volume times delta V. So I explained two things, condition and mass. So let me go through how we estimate PBH abundance. So previously, the obtained condition was written by some physical values. Those R was defined by the surface area of the bubble to be 4 pi R square at the collision. However, in order to have a PBH abundance, it is much more convenient to define some coordinates and play around in the well-defined coordinates. So now I will define some coordinates. Of course, FRW coordinates will be most familiar for us. So I will take coordinate R bar and T, where space-time metric outside the bubble is given by the FRW form. If I translate this condition into those coordinate system, then it corresponds to this blue band. I will not write down the equations because it is messy. But anyway, for a bubble nucleated at T1 to form a black hole, there should be another bubble nucleated within this band. That is what I mean by this band. But at the same time, we have another condition, which is that the collision area at the collision time should remain in the first vacuum to make a collision between these two bubbles. If not, they should have collided even before they collide at TC. So therefore, we can estimate the expected number of PBH formation for a given bubble nucleated at T1 you can integrate over this phase space of the bubble nucleation rate gamma n times the probability that a point remains in first vacuum until the collision time. Then we can integrate over the T1 such that in order to estimate the number density of PBH. So in the end, I explained all three things: condition, number density, and mass. So we are ready to estimate the PBH yield. But in order to estimate, we need to specify the parameter L over R here, and gamma and the bubble nucleation rate as a function of time, and delta V, the potential energy difference. Here is an example. I take gamma n as an exponential function. Excuse me, I cannot see the
5 minutes
yeah.
left, including discussion.
Oh, okay, thanks.
Yeah.
So here is an example. So we take an exponential function for the bubble nucleation rate. Here beta is a parameter, and L over R is taken to be 10 to the minus 3, and then we obtain this result. So here x-axis shows the PBH mass, and y-axis shows the PBH abundance normalized by the observed dark matter radius. So here I take beta from 6 to 12, and there are several constraints coming from search for black hole evaporation signatures and search for lensing signatures. And here you can read T star values from those small numbers, and where T star is defined roughly as delta V to the 1 over 4. You can interpret this T star value as reheating temperature or critical temperature or any characteristic scale corresponding to the phase expansion. And this numerical value 10 to minus 3 corresponds to the case where black hole forms when those colliding bubbles radius are required to be larger than 30 times Hubble radius. So you may wonder how small is such a probability to have a collision of such a large bubbles. Here I depict the number density times Hubble volume, and x-axis is log of L over R. So let's take some values. So if I take beta equals 6, then this means this y-axis is roughly 10 to minus 15. That means in 10 to 15 Hubble volume, we have one event of PBH formation. That is what it means in this estimation. So anyway, there are several more things to emphasize. Here Tn doesn't change the result because Tn just changed the time coordinate, and beta can be interpreted as an inverse of the duration of phase transition. And since we take the exponential function of gamma n, you don't have to worry about the eternal inflation in this case. Anyway, yeah, that's all I prepared. I think I exceeded a little bit time. So if you have any questions, please let me know.
Thank you very much, Tae Hyun, for your clear talk. Now it's open to questions and comments.
I have a question. So in your case, you need the bubble radius to be much larger than the Hubble radius to get the primordial black hole. Then means suppose the the bubble radius is smaller than the Hubble radius, you may have, I mean, the other limit, you may have bubbles created, at least one bubble in the Hubble patch. But if bubble radius is larger than the Hubble radius, then even one bubble, it's hard to create one bubble per Hubble patch. Then you have a small probability to create two bubbles in the Hubble patch, even smaller probability.
I understand your situation, but here the important part is that the bubble nucleation rate is not a constant. So your argument holds if bubble nucleation rate is given by Hubble to the 4. If you don't have this time dependence here, then you will have one bubble nucleation per one Hubble patch. However, this is a function of time. So in the early stage of the phase transition, this there is a small bubble nucleation rate, but there should be some bubbles nucleated much before when the bubble nucleation rate becomes Hubble to the 4th. Right? So those bubbles, I mean those bubbles that were nucleated in the early stage can become a large bubble in the end. So that is the scenario we are thinking.
I see. So in the beginning, you have sub-horizon sized bubbles created, and then they're growing, and then they're running, and then they start colliding when their radius is big enough. Okay, I see. Okay.
Thank you very much. Any other questions or comments? So maybe almost the time is up. So let's move on to the next presentation. Let's thank Tae Hyun again. So, okay, so Poyan?
Yeah. So I can share the file.
Yeah.
Can you see the slide?
Yes, I can see the slide.
Okay.
So, okay, next speaker is Professor Poyan Tseng from National Tsinghua University. Talk title is Correlated Signals of First Order Phase Transition in Dark Sector. Poyan, please.
Okay. Yeah, thank you for the introduction, and thanks Professor Hyun-Min Lee and the local committee for organizing this workshop. So today my title is some correlated signal from first order phase transition in the dark sector based on our recent work, collaborate with Professor Danny Mafatia. So the Higgs mechanism is very successful to give the mass to other standard model particle. So through the spontaneous symmetry breaking means the vacuum expectation value of the Higgs being transferred from the false vacuum to the true vacuum. So that implied in the early universe, it been through the electroweak phase transition around the few hundred GeV scale. And the other phase transition is the QCD phase transition due to the quark condensate. But both of them belong to this smooth crossover, but we are more interested in the more violent first order phase transition because it can give us the detectable gravitational wave signal. So in order to realize the first order phase transition, we need some effective potential which generate potential barrier to separate the false and the true vacuum. Therefore, quantum tunneling is required to transfer from one vacuum to the other. So therefore, we considering the first order phase transition may happen in the dark sector. And this scenario being discussed by many speakers in this workshop. Maybe yesterday the Cox and Eric also discussed this scenario where a fermionic diameter particle coupled to the scalar phi in the dark sector. So once the scalar phi obtains the non-zero expectation value, then the diameter becomes massive. And the scalar phi itself also generates the effective potential, which induce the first order phase transition in the early universe. Then the process of this first order phase transition has been very detailed described by previous speaker, Tae Hyun Jung. And so basically the bubble will nucleate in from the false vacuum, then bubble will quickly expand and occupy the entire space. So inside the bubble correspond to the true vacuum, so diameter particles are massive inside the bubble, but they will be a massless particle outside the bubble. So at the beginning, all the diameter particles, they are all located outside of the bubble. So they can either choose, either they penetrate the bubble or enter into inside of the bubble, or they can choose to remain stay outside of the bubble. So the first scenario, I think, will be covered by the following talk by the Shin, discuss about the bubble filtering diameter effect to determine the diameter Rayleigh density. And in this talk, I would like to focus on the second scenario where the diameter particle remains stay outside of the bubble. Then due to the expanding bubbles, the volume of the false vacuum will continuously shrinking. So that will compress and squeeze those diameter particles to form the macroscopic structure. So it could form some Fermi ball. Then once the Fermi ball becomes unstable, it is able to collapse into the primordial black hole. So this idea is being proposed by the Sang-Hong Jun and Shin's paper. And then after that, the formation of primordial black hole being discussed in Shin's following papers. So how do we keep the diameter particle stay in the false vacuum? So basically, you need to satisfy the energy momentum conservation along the bubble wall. So outside, the diameter particles are massless, but they follow in the thermal distribution. So some particles carry large enough kinetic energy, much larger than its mass inside the bubble, are able to penetrate the bubble wall to enter into the inside. On the other hand, those small kinetic energy particles just stay outside of the bubble. So therefore, we can set up our parameter which make the diameter mass much heavier than the critical temperature of the first order phase transition to keep the bubble trapping inside the false vacuum. Then due to the bubble expanding, they will aggregate and then form the macroscopic structure like a Fermi ball. Then additional conditions need to be satisfied in order to stabilize the Fermi ball. For example, the asymmetry between diameter and anti-diameter number density, or the assignment of a global U1 charge to the diameter particle to stabilize the Fermi ball object. And then we want to estimate what is the number density of the Fermi ball formation after the first order phase transition. So the T star here is the pre-collision temperature of the phase transition. So during the transition, the false vacuum volume will continue shrinking. The new bubble will nucleating inside the false vacuum volume until it reaches to the critical volume. So this critical volume is small enough such that there is no other bubble forming inside during its shrinking. So that will translate to this equality where the bubble nucleation rate multiplied by this critical volume and multiply the shrinking time should be equal to 1 or less than 1. Then after that, the material enclosed within this critical volume will be utilized to form the single Fermi ball. So once we obtain this critical volume, then multiply the number density of Fermi ball should give us the volume fraction of false vacuum at that time during the phase transition. Then we move the critical volume to the right-hand side, then we can estimate the number density of Fermi ball. Then after that, we also curious about, for a single Fermi ball, how many diameter particles constitute a single Fermi ball. So this being described by this quantity, the Q sub FB. So this is just nothing but the total diameter number density divided by the number density of Fermi ball. Then for the individual Fermi ball, we trying to understand what is their mass profile or the radius. So it can be obtained by considering the total energy contribution from several contributions. The first is the fermionic gas kinetic energy, and the second is come from the Yukawa potential, come from the Yukawa interaction with the intermediate scalar phi. The Yukawa interaction is always attractive, so Yukawa potential always carry a negative sign. Then the third one is the potential of the scalar field. Because the Fermi ball live in the false vacuum, so their potential is much higher than the true vacuum. Then by finding the minimization of the Fermi ball energy, that means the most stabilized condition of the Fermi ball, then we can determine individual Fermi ball radius and the Fermi ball mass. Then the Fermi ball rate density can be straightforward to calculate by multiply individual Fermi ball mass with its Fermi ball number density. The interesting things is come from this Yukawa attractive potential. The L sub phi is the interaction length of the Yukawa interaction, and it is inverse proportional to the temperature of the Fermi ball. So if the Fermi ball can cool down very efficiently, then this Yukawa interaction length will increase. Then until it reach to the average distance of the diameter particle separation inside the Fermi ball, then the Yukawa potential will dominate the entire Fermi ball energy. Then at that moment, the Fermi ball no longer stabilizes by itself, so the Fermi ball will start collapse into the primordial black hole. So in this scenario, the Fermi ball just treated as an intermediate state, then eventually it will collapse into the primordial black hole. So make my above discussion more concrete. So here I would like to specify the effective potential, because after that, it will dictate the following first order phase transition process, also describe the formation of the Fermi ball. So here we adopt a quartic effective potential. It's kind of model independent approach, but we included the temperature effect in front of the as a coefficient. And the capital D, capital A, and C, and the lambda, they are all the constant coefficient as our input parameter. So our strategy is first assign the value for this coefficient such that determine the following evolution of the effective potential, then we can calculate all the first order phase transition and the Fermi ball formation, or later on the primordial formation. So we choose the 8 benchmark point depend on the coefficient of the effective potential. Then the percolation temperature for this benchmark is around the kV scale to the MeV scale. So within this energy scale, the Fermi ball formation will give us the Fermi ball mass around 10 to the minus 6 to 10 to the minus 11 solar mass. And the radius could be comparable to our sun or much 10 to the minus 6 smaller than our solar radius. So the first impression for this Fermi ball is that the Fermi ball is not very compact object. It's not as compact as neutron star. Instead, it's rather close to our Earth's energy density. And of course, it's come from the first order phase transition, so it also generates some gravitational wave signal. So here is the gravitational spectrum from 8 different benchmark points. So their frequency vary from 10 to the minus 8 Hertz to 10 to the minus 5. So this frequency just able to be detected by future SKA and CA and the mu-Eris experiment. And another more direct signal from Fermi ball we considering here is the microlensing signal. So the Fermi ball can be treated as a gravitational lens, and we are the observer, and there are some background star moving around. So the light ray from the background star will be deflected due to the Fermi ball gravitational force. So the image will be distorted. But the Fermi ball is not very compact object. So most of the time, the separation angle of two images of the background star are too small to be resolved. But fortunately, we still can observe some sudden luminosity enhancement of the star. So this is called the microlensing. So for example, this Einstein radius being determined by the mass of Fermi ball and some geometry distance between observer Fermi ball and the background star. So once the background star flying into these open angles, its luminosity could be enhanced by 1/3 of its original luminosity. So that becomes a detectable signature from the astrophysical observation. So ideal observation is belong to this sky survey. For example, the Subaru Hybrid Supreme Can is a ground-based telescope observing our neighborhood M31 galaxy. So this picture showing the relative position between our Milky Way and the M31 galaxy. So both our Milky Way and the M31 being surrounded by the diameter halo, but in this time we just replace the diameter halo by a Fermi ball object. Then the commission time for Subaru is about 7 hours. So during this 7 hours, if any of the Fermi ball flying in front of any of the star in M31, it will suddenly enhance the luminosity. So that is the smoking gun signal for the existence of the Fermi ball object. So first of all, we need to estimate for certain Fermi ball mass how many events could be generated during this 7-hour observation time. So we use this differential formula to estimate the event rate. So here the F sub dn is the Fermi ball abundance fraction to the total diameter Rayleigh density, Rayleigh abundance. And the first term in the bracket is taking into account that the Fermi ball belong to our Milky Way, and the second term is the Fermi ball belong to the M31 galaxy. Then we performing some multi-integral to obtain the total event rate we can observe during this 7-hour observation time, and including all the available stars, about 100 million stars. in N31. So this is the total event rate contribute from the Fermi ball. So compare with the real observation from Subaru, they only observed one event with the luminosity enhancement. So statistically, we can translate into 95% confidence level that the Fermi ball contribution should be less than 4.7 event. So this gives us very severe constraint for the abundance of Fermi ball, such that if the Fermi ball mass range is around 10 to the minus 12 solar mass to 10 to the minus 5 solar mass, the Fermi ball cannot be 100% as a diameter candidate. Instead, the fraction of Fermi ball should be below this color curve. A different color curve indicate the different size of the Fermi ball object. But if the Fermi ball is from the first order phase transition, in this case, most of the Fermi ball radius is much smaller than the solar radius. So we can just use the brown curve in this plot. And the 8 benchmark point I show you in the previous table is distributed around this parameter space. So they are currently satisfied the Subaru current observation, but in the future, in the right panel, if the 10 times mode observation can be made in the future, then the sensitivity will improve, and such that all these 8 benchmark point can be tested in the near future. Another signal could come from the relativistic degree of freedom, because the phase transition temperature is very low. It's around the keV to MeV scale. So energy, so it's much lower than the Big Bang nuclear synthesis temperature. And there exists a very robust limit about delta N effective should be less than 0.5. So from the dark sector, we have 4.5 degree of freedom come from the fermionic diameter chi and chi bar and the one scalar. And here we considering the decoupled dark sector and the Stern-Mao sector, so their temperature could be different and been described by this ratio. So overall, we able to calculate the delta N effective. So still satisfy the current upper limit 0.5, but this value is very easily to be tested in the very near future experiment, like a CMB4S experiment have the sensitivity. Okay. Then the last part of my talk, I would like to consider in the primordial black hole. So the Fermi ball is treated as an intermediate state, and after Fermi ball collapse, it will form the primordial black hole. So again, we first specify the coefficient value of the effective potential, then calculate the first order phase transition temperature. But in this case, we would like to use slightly higher phase transition temperature above MeV scale. So in such case, the corresponding primordial black hole mass become much lighter, around the 10 to the minus 16 solar mass to 10 to the minus 20. So this mass range of primordial black hole will exhibit the significant Hawking emission. So that become a detectable signal for this primordial black hole. Okay. But the first still come from the first order phase transition, so it generates a gravitational wave spectrum shown here. Because this benchmark point carry the higher pre-collision temperature, so their gravitational wave frequency slightly shifts to higher frequency around the 10 to the minus 7 to 10 to the minus 4, but it's still being covered by the SIA and the New Eras experiment. Then about the black hole Hawking emission. So the temperature of the corresponding black hole mass around 10 to the minus 18 is about MeV scale. So most of the particle emit from the primordial black hole is electron, positron, and the photon. And interesting is when the primordial black hole mass is less than 10 to the 20 solar mass, the primordial black hole cannot survive until today. They will already evaporate. And the Hawking emission is being calculated through this formula, taking into account some gray body vector spectrum. There exists some public available code called the Black Hawk. Then they can automatically calculate the primordial and the secondary particle emissions. So we are focused on the signal from extragalactic gamma ray background due to the primordial black hole evaporation. So once we know the emission evaporation spectrum, then we can integrate the entire time from the CMB epoch to the current epoch and take into the account the redshift of the spectrum energy, so we can obtain the energy spectrum today. So this is the extragalactic gamma ray spectrum from this primordial black hole according to this 6 benchmark point. So their spectrum is around the MeV energy scale. So compare with several gamma ray observations, the dashed line indicate the current sensitivity, and the solid curve indicate the future sensitivity. For example, the omega X and the E astrogram. So most of our benchmark point can be tested by these two experiments. Okay. So let me summarize my talk here. So we discussed two scenarios of fermionic diameter undergo the first order phase transition induced by the quartic effective potential. So the scalar field give the mass to the diameter particle, and at the same time induce the phase transition, generate a gravitational wave signal. Then we trying to keep the diameter particle trapped inside the false vacuum, and the particle will aggregate to form the macroscopic structure. And if the Fermi ball mass is around the 10 to the minus 12 solar mass to 10 to the minus 5 solar mass, so this parameter space will give the gravitational wave frequency around 10 to the minus 9 to 10 to the minus 5 Hertz. And from the Fermi ball itself, we can directly measure it through the microlensing effect. And then if the Fermi ball temperature can be cooled down very efficiently, then the Fermi ball no longer stable due to the attractive Yukawa potential. Eventually, the Fermi ball will collapse into the primordial black hole. And we found the parameter space for the effective potential. It will generate the primordial black hole mass around 10 to the minus 20 to 10 to the minus 15 solar mass, and the corresponding gravitational wave frequency about 10 to the minus 7 to 10 to the minus 4, and associated with the extragalactic MeV gamma ray signal from the Hawking evaporation. Yeah, that's all of our results today. So thank you for your attention.
Thank you very much, Pyongyang, for interesting talk. Now it's open to questions and comments. Any question or comment?
I have a question. It's very interesting talk. So can you distinguish between primordial black hole and Fermi ball cases?
Yeah, in our case, maybe just primordial black hole is much smaller size because it already collapsed. So then the signal we consider here just the evaporation of this primordial black hole. So that will induce the gamma ray gamma ray signal. So this is come from the primordial black hole. With the Fermi ball, the size is larger. Then, yeah, basically the main signal is come from the microlensing. So, yeah, microlensing, yeah, depend on whether we see microlensing signal or a gamma ray signal, we can distinguish these two scenarios. Yeah.
Okay, so in the case of Fermi ball, I mean, in the case of primordial black hole, you want the say, you said the Yugawa potential becomes important when the temperature drops.
Yeah.
To form the primordial black holes, right?
Right.
But that means the nucleation temperature for primordial black hole might be smaller.
Oh, yeah. The temperature will be slightly smaller, but the process is that first, due to the first order phase transition, the Fermi ball being formed in the beginning. Then depend on the cooling mechanism of the Fermi ball, then the Fermi ball temperature will be dropped to certain lower temperature. Then if the temperature can be reached, then the primordial black hole can be formed.
I see. It depends on the cooling mechanism for the Fermi ball. I see. Okay, so independent, independent from the critical temperature for the phase transition. Okay, thank you.
Yeah, thank you for interesting question. Yeah.
Any other questions or comments? So, can I ask one question?
Sure.
So the fermionic dark matter forming a Fermi ball, what is the mass range of this fermionic dark matter? I'm wondering in the fermionic ball energy, you seem to ignore the gravitational potential in the fermionic, gravitational potential. Did you ignore?
Gravitational is come from the first order phase transition case. Yeah, for the diameter mass is the G chi here is the Yukawa coupling.
Right.
So if they multiply with this vacuum expectation value, it give the mass to the diameter particle. So it's roughly. Sorry. Yeah, this is not the vacuum expectation value. Yeah, the vacuum expectation value is close to the percolation temperature. So here is around the MVV scale, then multiplied by the coupling.
I see. So maybe gravitational interaction is safely ignored in the fermionic ball energy.
Yeah, it's negligible because it's macroscopic object. So the gravitational force is not dominate in this term. Yeah.
I see. Microscopic.
Macro, yeah.
Macro. Macro.
Yeah, it's a huge object. Yeah.
A huge object.
Yeah, size is comparable to our sun. Yeah.
I see. Huge. I see. Energy density, mass density is small.
Right.
Thank you very much.
Thank you.
Thank you very much. Time is up, so maybe we want to take a break. So I think Professor Hyun from, I'm not sure, 11 session. The first speaker is Professor Shin from Chungnam National University. Talk title is Dark Matter Filtering Out Effect during a first order phase transition. Chang-san, please.
Yeah, thank you for introduction and invitation. I'm Shin from Chungnam National University. Today, I'd like to talk about the dark matter filtering out effect during a first order phase transition, which was done with Tae Hyun, the previous speaker, and Dongjin Choi in IBS. All right. Okay, so this is the outline. So I will first introduce my personal motivation for thermal heavy dark matter scenario 2 years ago at that time for this work. And also discuss the dark matter genesis mechanism that we proposed and then related conditions for the successful realization of the correct dark matter density. So let's start. Since we don't have any strong hints for the dark matter mass, especially for the mass range of WIMP dark matter, various mass range of dark matter is actively studied as given by in various talks. And also for different mass values, there are different production mechanisms. For very, very light wave-like dark matter candidate and for very heavy the macroscopic dark matter candidates, the gravitational interactions are generically more relevant for their abundance. Meanwhile, for the intermediate mass range, so particle-like dark matter case, the interaction between the dark matter and the standard model thermal mass could be more relevant to determine the dark matter density, especially using through the freeze-in or freeze-out mechanisms. So heavy dark matter in this talk correspond to the particle-like dark matter, whose mass is hierarchically larger than the weak scale, but still smaller than the Planck scale. And we want to focus on the role of the interaction between dark matter and thermal mass for the evolution of this dark matter. So my concern is thermal dark matter. And as discussed in yesterday's talk, there is some famous unitarity bound for thermal dark matter. So in the early universe, the dark matters in thermal equilibrium through the various scattering with a background thermal plasma. And then as temperature decreases, it will gradually depart from the equilibrium line, follow the from this Boltzmann equations. And as you can see, this density of the dark matter, it is less sensitive to dark matter mass itself, but more sensitive to the annihilation cross-section. So this is one of the key features of the freeze-out dark matter model. However, the annihilation cross-sections is also bounded by dark matter mass, as noticed by Grist and Kamiokovsky a long time ago, given by this formula. Therefore, as the dark matter becomes heavier and heavier, it is inevitable that upper bound of annihilation cross-section times my mass increases. So if the mass of the dark matter is much hierarchically greater than several 100 times TeV scale, then it is the corresponding energy density of the dark matter should be much greater than some order 1 value. So in this sense, thermal heavy dark matter is not favored. But still, the heavy dark matter scenario is quite appealing because it is still the attractive source of the unidentified high energy cosmic ray when it is a decaying dark matter. So it can provide some hint for the interaction between dark matter and the standard model particles. So about the hint about the production mechanism. And even if the dark matter is absolutely stable, so it does not produce any decaying product, it still could provide interesting phenomena when there is a sizable interaction between dark matter and the standard model particles. So regarding that, I would like to refer to one paper done by this author. So basic idea is the following. So if there is a sizable interaction, the cross-section between dark matter and some ordinary standard model matters, then it could be captured by star, especially if we consider white dwarf, then this dark matter could be accumulated after thermalization at the core of the white dwarf and can form some black hole. So because the small mass of this black hole, it can evaporate with some given Hawking temperature. And please note that this temperature is proportional to the positive power of the mass. So when the dark matter mass becomes larger and larger, the corresponding Hawking temperature also becomes higher. So it leads to some effective spark for fusion reaction for type 1a supernova explosion, and leads to some deviation from the standard type of a supernova explosion process. So this actually, although all this process depends on the more detailed property of the particle, dark matter particle. However, this, in my opinion, this would be one interesting example of the motivation for the motivation to study heavy dark matter with a sizable interaction between dark matter and the standard model particle. On the CRA side, there are also many studies to reduce the thermal heavy dark matter density. So of course, the easiest, the universal way is to dilute dark matter by entropy production. So in many SUJI models, it is quite natural to have some large vacuum expectation value of the scalar fields compared to its mass scale. So like this, some stretched scalar potential. Then at high temperature, because of the interaction with the background of thermal plasma, the universe could be trapped at the origin of the this field space. This is a minimum of the free energy density, including all possible thermal correction. And as temperature decreases, this global minimum values gradually increase, and some new global minimum is developed. But because of the large width between here and here, it leads to small nucleation tunneling rate. So it is still trapped at the origin, but eventually there is a phase transition and the universe would be reheated. So during this process, there is some vacuum energy domination era, and it leads to some supercold period. Therefore, after reheating, some large entropy would be produced. So this provides some suppression of the dark matter yield due to the some large production of the additional entropy during the reheating process. But it is not actually for some special for thermal dark matter. So regarding that, a more concrete idea considering the origin of the dark matter mass was discussed a long time ago in this paper. So the large mass of the dark matter could be related with some large symmetry breaking scale. So it also could be related with some cosmological phase transition in the early universe. And from these observations, also can naturally relate to dark matter mass and the phase transition. And then the thermal history of the dark matter is also well determined from the beginning at some thermal equilibrium value. So they can successfully calculate the final dark matter yield value with some correct suppression factor. And the other recent study in this paper also discussed the additional production mechanism for dark matter from the thermal bath after reheating, so-called thermal production. Its effect can be inferred from this Boltzmann equation with this equilibrium value. So this could be a source of the additional production of the dark matter, whose value is proportional to e to the minus 2 times m chi over T reheat. So all these works actually discuss the relation between dark matter radiative density and the phase transition, but they are basically more about the second order phase transition. So scalar field value would be smoothly changed from the zero value to the finite value. So totally different approach, which was also discussed yesterday, is utilizing the chain of the coarse scatterings of the these dark matter ensembles to reduce the heavy dark matter density. For me, this idea could be interesting because the production mechanism of dark matter itself could explain the instability of the heavy dark matter. So heavy dark matter could decay and produce high energetic cosmic ray because it's a production mechanism. So, right, so including also other recent work during 2 years, the summer heavy dark matter scenario is still a very interesting possibility. So in this talk, I'd like to focus more on the role of the phase transition, especially the first order phase transition for stable summer heavy dark matter, whose mass is given by the order parameter of phase transition. So such a consideration also can provide interesting relation between the gravitational wave observation and the heavy dark matter scenario. So although I will not discuss the details about this gravitational wave production, but as Poyan discussed some several interesting examples, you can easily imagine there could be some interesting correlation between two observations. All right, so now I will introduce some so-called filtering out mechanism for thermal dark matter, whose basic idea is shared by these two papers. So at the early universe, if there is a phase transition and phase transition is the first order, then after phase transition, there is some bubble formation. So at a certain temperature, so-called nucleation temperature. And these bubbles will expand with a certain velocity. So with a world velocity psi w. And during this bubble expansion, the most of standard model particles can easily enter the bubble because there is no any special interactions, while the most of dark matter is reflected because it needs a large energy to overcome the rest mass energy inside the bubble. And only a few dark matters can enter the bubble. And actually, this dark matter is what we observed present. So this is the basic idea. So in these situations, the dark matter is massless outside the bubbles, and it has some sizable thermal interaction with the background plasma, right? So its number density outside the bubble is just given by this one. So mainly as the function of temperature. However, the dark matter density inside this bubble is not only the function of the temperature, but also the function of the mass inside the bubble, and also bubble the dark matter flow velocity v tilde in the world rest frame. So it would be generically some complicated form, and this is the corresponding number density of dark matter, which has some rather complicated dependence of the dark matter flow velocity. But it becomes simpler if we take a non-relativistic limit or relativistic limit. So it has, of course, different the exponential suppressed term, but it basically anyway reflects some filtering out effect. So it is the origin of the suppression of dark matter density. And this filtered dark matter number density is just frozen because of the low temperature inside the bubble and also very small abundance of the dark matter. So as the analogy of freeze out mechanism, we call it the filtering out mechanism, or just a filtering out process. So then if we consider this scenario very seriously, then there could be so many questions about the detailed processes. First of all, how can we determine dark matter this flow velocity V tilde. And also, what's the bubble wall velocity psi W for given equation temperature and given model parameter. And then what is the fate of this reflected dark matter like this one? And also, what's the effect of bubble collisions? I mean, dark matter could be reproduced if this local hot plasma temperature is high enough. And it could spoil the filtering process. And what is the necessary condition for the scalar potential for successful phase transition? So I will discuss the answers to this question in the remaining part. For first and second questions, in our work, we take a rather simple assumption based on that dark matter has a sizable interaction with a thermal plasma. So it can easily go into the thermal equilibrium value outside the bubble. So the assumption is following. The dark matter particles interacting with the bubble walls can instantly, which means that within some microscopic time scale, exchange their energy and the momentum with the ambient thermal plasma. And those plasma could be well described by perfect fluid approximation before some macroscopic event of the bubble collision. So then following the strategy given by this paper, we could calculate this thermal plasma, the energy density distribution and velocity distribution around the bubble wall for given terminal velocity of the wall psi W. So in general, there are three classes of the thermal plasma distribution around the bubble wall. So if this wall velocity is greater than sound speed, then most of the energy of the plasma would be accumulated just behind this wall in the broken phase. On the other hand, if the wall velocity is smaller than the sound speed, then the plasma energy density is mostly accumulated in front of the bubble wall. So the corresponding the relative velocity of the plasma, V plus and V minus, outside and inside the bubble wall in the wall rest frame would be different for different situation. So anyway, before determining this wall velocity, here we have one crucial simple assumption. That is, so dark matter flow velocity which hit the wall, V tilde, is given by the fluid velocity in front of the bubble wall, so V plus. And also dark matter temperature is given by the fluid temperature, T plus. So actually, this is the role of the interaction between dark matter and standard model thermal bath. So through this simple assumption, we could calculate the number density of the dark matter inside the bubble, even if the bubble velocity is ultra relativistic, right? And then the next question is, what is the bubble velocity? So okay. So in order to calculate the bubble velocity, we have to compare two pressures. So one pressure is given by the vacuum pressure originate from energy difference between forced vacuum, true vacuum, and the forced vacuum. And there is another pressure induced by dark matter, this reflection event. So in the minimal consideration, most of the standard model particle will just enter the bubble, so does not contribute to the pressure to the bubble wall. So only the important contribution is coming from the dark matter flow. So for given dark matter velocity, V tilde, we could estimate the corresponding the pressure induced by this dark matter bubble wall scattering. And it has some special feature depending on this dark matter velocity. also depending on the relative hierarchy between the dark matter mass and the temperature. So in our consideration, for successful filtering out process, so we want to consider a case that dark matter mass is hierarchically greater than temperature. And also dark matter mass is hierarchically greater than the boosted energy induced by this velocity. So gamma times the temperature. So that corresponds to the this region. So given labeled by these two. And for that region, we could calculate it, the velocity dependent pressure value from the fact that most of the dark matters are reflected from the bubble world. And by evaluating the equation P chi equal delta V, so we could obtain the terminal velocity of the bubble world and terminal velocity of this dark matter flow. So terminal this Lorentz boost factor. So actually here we found that in most working parameter space, this terminal Lorentz boost factor is hierarchically greater than 1, which means that the bubble world velocity is ultra relativistic. So then what's the implication of this ultra relativistic bubble world? This means that we also have to consider carefully the effect of a bubble collision, because there is some two ultra relativistic bubble world, which means that there are two ultra relativistic plasma behind the bubble world. So when bubble world collide, those two ultra relativistic plasma also will collide each other. And then perfect fluid approximation would be broken in this scattering cross section, and would be locally heated with this temperature T max. And then our conservative bound on this local maximal temperature is that it should be hierarchically smaller than usual freeze-out temperature of the dark matter. So the regeneration of dark matter from the thermal bath by pair creation should be ineffective. That is our criteria. And then we could calculate this maximal temperature from this fluid motion. And it turns out that this maximal temperature is parametrically smaller than this gamma W times the nucleation temperature. And for the successful the filter out process, this gamma T also should be smaller than this dark matter mass. So this means that if this filtering out process is efficient when dark matter interact with this bubble world, then the maximal temperature from this bubble collision T max is naturally smaller than this effective freeze out, naive freeze out temperature for the this dark matter. So this means that the thermal production from the this local hot plasma is subdominant. So we don't need to worry about its abundance. So considering all these effects, also including some dilution factor due to some super cold period from during the phase transition, we get a following formula for the dark matter energy density. And as you can see in this formula, so even if the dark matter mass is very large compared to weak scale, thanks to the this exponential factor, also due to the large dark matter mass, leads to the correct dark matter density. So for variety of the dark matter mass is allowed through the this filter out mechanism. And if we fixed this observed value of the dark matter density, then certain combination of the model parameter also would be fixed. And then we can scan the available model parameter in this parameter space. So here we take two important dimensionless parameter to scan the allowed parameter space. So one is the alpha n, the other is lambda effective. So I will explain the physical implication of alpha n and lambda effective. So large alpha n actually means that the force vacuum energy density is large compared to background energy density. So it leads to more longer supercooled period. And a large lambda effective implies that it provides a large vacuum pressure because of the large delta V.
5 minutes
So,
left for including discussion. 5 minutes.
Thank you.
Yeah.
Yep.
Left.
So here we could obtain this allowed range, and this rainbow colored region is actually turned out the parameter range that filter out if effect is dominant. And as you can see on this range, different dashed line correspond to the different dark matter mass to satisfy correct dark matter density. So you can see various heavy dark matter mass could be allowed through the filter out process. And it leads to some certain combination of these two model parameter, lambda effective times alpha n should be around 10 to the minus 9 or 10 to minus 10. So that is the some successful parameter range for the filtering process. And then I will shortly mention whether or not such a kind of a parameter value could be realized in the realistic model building. Here, I just want to emphasize that we consider the minimal setup. So there is various possibility to determine bubble wave velocity. And in this minimal setup, we study some supersymmetry model, especially some gauge mediation model, which means that the scalar potential is dominantly given by some gauge mediated mass term if field value is smaller than some messenger scale. While if field value is much larger than the messenger scale, the gravity mediation also could be effective. Then the small value of these two combination lambda effective alpha n is given by the linear hierarchy between the gravitational mass and this messenger scale, this soft breaking scale. So this condition could be easily realized in certain this kind of a model building. Right. So this is my last page. So although the unitary upper bound on the mass of the thermal dark matter is robust in some sense, thermal heavy dark matter scenario is a very interesting possibility. And mass of dark matter could result from the symmetry breaking effect, so could be related with a cosmic phase transition for their number density and energy density. And then first order phase transition can provide a filtering out effect for the heavy dark matter Rayleigh abundance, so allowing a wide range of the dark matter mass beyond the unitary bound. And gravitational wave could be generated from this first order phase transition, which can provide some further information about dark matter mass and its interaction strengths. And also there are many questions that I didn't answer in this talk about what's the correct transport equation for dark matter and solution around the ultra-relativistic bubble world and the fate of the dark matter confined in locally in the symmetric phase just before the bubble collision, and also possible dark matter evolution after bubble collision. So and including model beam. So this is the end of my talk. Thank you for listening.
Thank you very much for valuable contents, Chan-san. So it's open to questions and comments. Any question or comment?
I have a question. So you listed several questions, some issues for filtering mechanism. So one of them is the bubble collisions that you discussed in the later part of your talk. So, so in the case you want to preserve the prediction for the filtering mechanism. Is it is it also possible to have a sizable dark matter production during the bubble?
Sure. From, you mean this part, right? So basically there could be two possibilities. If the this is a runaway bubble world, or it's anyway Lorentz perspective is very large, then in some case, from the bubble collision, in this local place, the symmetry could be restored. So dark matter could be massless, and so a lot of dark matter abundance could be also produced. And in this case that I consider is that there is no such kind of symmetry restoration, but still dark matter could be produced from the this local the plasma. Of course, then abundance is basically smaller than naive unitarity bound. Yeah, that is also a possibility. Maybe we provide some different naming, but I think there are some work about this possibility, but I don't remember correct paper.
So maybe I don't know if the bubble world energy is transferred to the local plasma, dark matter plasma, such that it could penetrate into the false vacuum, true vacuum. Sorry, because we are producing locally dark matter particles at the bubble walls, and then what is the fate of this local energy density? Does it penetrate into the bubble wall, or does it how does it although I guess you assume that the local temperature, initial local temperature to be small enough such that there is no large penetration, right, of the dark matter particle into the true vacuum. But if I don't know, the temperature also depends on the bubble collision energies, and there might be some correlation with the gravitational wave signal or something like that. So in your case, in your estimation, you assume that the local energy density is small enough, right?
So small enough not to provide any background change.
And also, it's local in the sense that it is concentrated on the overlap of these two bubbles. So there's a limited phase space in this case. Instead of it's not homogeneous energy density. Instead, in this case, it's a kind of concentrated. And I don't know, maybe similar to what Tae Hyun said in his talk, although it is different. I mean, it talked about primordial black hole formation and this local energy density, but I don't know if it might be sufficient enough to get primordial black hole, but also could produce a lot of dark matter particle. I don't know.
That would also possible. So although I missed some Taehyun's talk, most of the part, and I don't know whether or not his parameter space is the same as this case. But at least in this case, that the maximum temperature is low enough, so there we expect there is no some more energetic process. But in general, there could be such kind of effect, especially supercooled phase transition. So I don't.
I agree. Yeah, because you are focusing on the supercooled phase transition.
Right. So Tae, do you have any?
So can I add a comment on this?
Sure.
So in order to form a black hole, what matters is actually the radius of the bubbles. So if the radius of bubbles can be as large as like few tens of Hubble radius, then this collision region will become a black hole. However, in Chang's study, he is considering much smaller bubble. So the radius is much smaller than Hubble radius. So I don't think a black hole can be formed in typical cases.
I see.
So in most cases, the picture will be described by what Chang explained. That's my guess.
Yeah, thank you for comment. So it depends on size of a bubble, and in our consideration, size of bubble is generically sub-horizon. So
Okay, thank you.
Thank you very much for nice discussion. Actually, time is up. So let's thank Chan-san again. And let's move on to the last speaker of morning session, Professor Seong Park. So could you please share the screen?
Yes, just a second.
Yeah. Yeah. Now he entered the room again, Zoom room again.
Okay,
I can see the screen. Yeah. Yeah. So the last speaker in the morning session is Professor Seong Park from Yonsei University. Talk title is Primordial Black Hole and Gravitational Wave in Higgs R2 Inflation. So, Professor Seong Park, please.
Thank you very much for the introduction. And I'm very sorry for making a lot of trouble this morning. Yeah, this morning was terrible for me. So anyway, so I want to talk on Higgs R2 inflation today. This talk is based on several works done by myself and with my students, Dong-Hyun Chang and Sang-Muk Lee and many others. So please take a look at those released in later on. So let me introduce Higgs R2 model first. The Higgs R2 model is an effective field theory model based on the standard model Higgs field and gravity, with the terms R, the Ricci scalar, and the non-minimal coupling term of the Higgs and the Ricci scalar H square and R, and plus R square and so on. And probably we can also include higher order terms, but in this talk, I'm gonna focus on up to the R square term. And this model is generated to provide the successful cosmological inflation. And indeed, this model seems to provide the best fit to the Planck data. So I'm excited. And this model still keeps the all virtues of the standard model. For instance, electroweak symmetric breaking is produced by the Higgs field, the known Higgs field in the standard model. When you take the RG running effect, we can understand this particular combination, Higgs self-coupling over non-minimal coupling squared is 10 to the minus 10 during inflation. That is naturally understood. And the perturbative unitarity with a high cutoff scale of this Higgs R2 inflation is given by this combination. And Planck times the factor and Planck squared over Cauchy squared times scalar mass squared. And this combination can be easily larger than order 1 when the scalar mass is lighter than a certain value. I will come back to this issue later. Okay, so this model is theoretically well motivated and theoretically well behaved at the UV scale. So we can really play with this model. And the potential. Yes, please.
I'm sorry. Yeah, okay. So here, I guess you also have another pre-parameter, the coefficient of R squared term.
That's right.
And my question is then effectively you introduce extra degree of freedom, the scalars, right? In addition to the model.
Yes.
But in that sense, this is not truly the minimal standard model, but you have some extra scalar degree of freedom, which plays a quite important role for the inflation. Is it correct interpretation?
Yeah, that is right. In a sense, R square inflation itself provides extra scalar degree of freedom.
Right, yes.
We can think of dual description in a sense. Okay.
So, but you say that, okay, for instance, this cutoff scale lambda is independent of the coefficient R squared term.
Well, the coefficient of R squared term is actually related with the mass of the scalar.
Okay, that's right. Okay, thank you very much.
Thank you. So let me move on. And the potential in this model, or Higgs R2 square, R square model, has a very interesting shape, and it provides interesting enhancement in curvature perturbation and also isocurvature perturbation, depending on the model parameter choices. And once this enhancement in the curvature and isocurvature perturbation takes place, we can find the sizable production of PBH and also gravitational wave. Okay, and even more interestingly, the produced PBH is in the right window of the dark matter of the universe. So I will explain this part also later. As you can see, this model links the electroweak scale physics, well, Higgs physics, and the inflationary scale physics. Well, we are talking about inflation with a common field, Higgs. So we can learn from both sides, particle physics at colliders and cosmology and astrophysics. So this setup is fairly interesting in both approaches. Okay. So let me begin with the Higgs in the standard model. As we know, the Higgs is the only observed elementary scalar particle so far. Okay. And the Higgs is given by this particular quantum numbers, the singlet of SU3 and doublet of SU2, and it has 1/2 hypercharge, so that we can write down Higgs in this way. Then you can see two goldstones, G plus and G naught, upside and downside of the doublets, and the upper part of the goldstone is eaten by the W boson, and the lower part of goldstone is eaten by the Z naught. So in the unitary gauge, we don't have to take those goldstone degree of freedom, but we still have the physical degree of freedom, neutral Higgs, and which is nothing but the particle observed by the LHC some years ago, and still the parameters are better measured. And we also have the vacuum expectation value of the Higgs, and which is responsible for electroweak symmetry breaking, as well as the masses of elementary particles in the standard model. Okay. So having this SU2 doublet Higgs, the most general gauge invariant renormalizable potential includes only two parameters. One is Higgs self-coupling, lambda, and the other one is V, the vacuum expectation value of the Higgs. Okay, and in unitary gauge, you can expand this potential in terms of the physical Higgs. Then you can find Higgs quartic term given by this, and cubic term given by this, and the mass term given by this. And here V, by the way, is determined by Fermi constant, and that is 246 GeV in the standard model, and the lambda, which is determined by the Higgs mass 125. Then you can calculate this lambda is around 1/8 at the electroweak scale. Okay, so all the standard model free parameters are already measured by the LHC. So this is the measured potential of the Higgs, and you can see, as you can see, the first term is predicted to be 1/32, and second cubic term is predicted to be 246 GeV/8, and the mass term is measured. So checking this quartic term and cubic terms are the most important task for the future collider experiments to confirm the standard model Higgs. Okay, and the Higgs in the standard model is responsible for the mass of elementary particles, And this linear relation, the mass of the particle is proportional to the Higgs VAF, and that is beautifully confirmed by LHC. So up to the top from the mu1 has all measured with the excellent precisions. And I'm very happy to see this mu1 coupling is consistent with the standard model within 26%. And this number will be improved in the future. Okay. Taking this measurement near the electroweak vacuum, we can also think of the global shape of the Higgs potential. Okay, so here in this effective potential, I want to include the dark energy and the quartic term. And the mass term is not that important in the low energy, but that can also include it. And then we can think of high order terms, H6 and H8 and so on and so forth. They are all gauge invariant. Okay, so taking all these terms into account, we can imagine the shape of the potential like this. The first, the shape is given by the well-known the Mexican hat shape, and it has the unique vacuum here, 246 eV. But we can also think of the second type of the shape, which depends on the RG running of the lambda, which can be pretty small at high scale, even negative at some point. Then we can include the higher order terms, so we can still see the turnover of the potential. Okay, so we have, so if we take the first case, we have a unique vacuum, but in general, we may allow the second vacuum at the UV, and the vacuum value can be even in the ADS. Okay. It is interesting to think of the Higgs potential taking the digital vacuum, so which seems to be consistent with the current cosmological observations. So in the digital space, we can actually find very interesting bound in mass of charged particle. This bound is called Festina Lente bound, suggested by the Vafa and his company recently. And in here, they consider the charged black hole in digital space and its decay through the Hawking radiation. So indeed, when we consider the charged black hole in digital space, we can find the phase diagram of the charge and mass in this shape. This shape is called shark fin shape. And in this shark fin shape, we make think of the physical black hole within this phase diagram. So we cannot go outside of this phase diagram. Okay, and then taking the Hawking radiation into account from this phase diagram, they found an interesting bound on the charged particle in the theory. Okay, that is given by this inequality. The mass of charged particle to the 4 has to be larger, greater than 8 pi times alpha times q squared times v. This v is the vacuum energy of the theory. Okay, and I can talk more on this, but I just show you this bound. Okay, later if you are interested in, we can discuss more. Okay, so this is the bound found by this paper. So then we can apply the shape of the Festina Lente bound for the Higgs gravity system. Okay, so now let's think of the Higgs gravity system with cosmological constant. Okay, so here, of course, we can include the other standard model fields as well. So first of all, if we think of the electric vacuum locating here, we can set the bound on cosmological constant of taking the Festina Lente bound. Okay, so please remember the charged particle mass of the charged particle to the 4 is limited by the vacuum energy, and so from that consideration, we can find the size of cosmological constant should be less than G times, me to the 4. Here, me is the mass of the electron, which is the electron is the lightest particle among all charged particles within the standard model, and alpha is the fine structure constant. So plugging in the measured values of G, me, and alpha, we can find cosmological constant should be less than 10 to the minus 90 of m Planck squared, okay, at the electroweak vacuum. And that is consistent with the observational value for the cosmological constant, 2.8 times 10 to the minus 122 m Planck squared, okay? So this seems to be okay. And then we can apply the other case, the Fresnel antibound, to the other cases as well. So if we the Higgs potential allows the second vacuum, which at the UV vacuum expectation value, we can apply the same Fresnel antibound using this standard model expression. Okay, and then the standard model mass, the mass of the charged particle to the mass to the 4 is limited by the vacuum energy. Then from this consideration, we can find the effective Higgs self-coupling at UV scale has to be limited by the Yukawa to the 4 over 8 pi times alpha. That is nothing but 10 to the minus 22, taking the RG running effect of the standard model. Okay, so having this value, if the second vacuum really exists, it seems the shape of the potential could be pretty degenerate with the electroweak vacuum at high scale. Okay, so now let me expand the theory to include other terms as well. So here I want to include 2 more terms. First term is the non-minimal coupling term, 2 times HH dagger, and the R squared term here. Okay, as Kyun asked in the beginning, here the coefficient of R squared term is given by this combination. This is dimensionless, right? And here M is the mass of the scalar run, which I will show you later. Okay, so please note the first term has the exactly same dimensionality of M Planck square. Okay, and the last term is the mass to the 4. So they are consistent with the standard model gauge symmetries and also Lorentz symmetries, and has the right dimensionalities. Okay, so in a sense, those terms are naturally appearing in effective field theory. And indeed, if you turned off those terms in the beginning, if you take the loop effects into account, those terms reappear in the theory. So you are not allowed to get rid of those terms by hand. Okay, you can add more terms like Gauss-Bonnet term that can also contribute to the global structure of the theory, but they do not contribute to the local structures. So I don't take this Gauss-Bonnet term in my study. However, I also note if Gauss-Bonnet term has a non-minimal coupling term like that, then this can show up in observables. So that can be interesting. Okay, and also I mentioned earlier, high order terms like R cubed term, R fourth term, and so on can be included, but here they are neglected. Assuming the coefficients are tiny, small. Okay, but it turned out that they can be also important when we consider high scale physics. Okay, so now we have a setup. To go into the Higgs R2 inflation, I briefly mentioned the non-minimal coupling and its implication to the inflation first. So here we can think of this non-minimal coupling term K, that can be anything, right? And V is a potential, and that can be anything as well. Okay, and from this theory, non-minimally coupled scalar theory, we can recover the Einstein the theory in Einstein frame, taking the Weyl transformation given by this, and this conformal vector is given by this vector m squared plus k over m Planck square. Then after this Weyl transformation, you recover the action in Einstein frame and find the potential in Einstein frame is nothing but this. Okay, here V is the original potential, K is the non-minimal coupling. Okay, so if we take interesting case when K is monotonic function and also V is a monotonic function, then you can easily see that this potential in Einstein frame becomes constant at high scale, right? Because this K term overtake the M squared term in the in large field limit, and then we only see this combination in Einstein frame. Okay, and so this is the condition for the flat plateau at high field limit. Okay, so taking this general condition into account, we can consider this kind of toy model with the monomial functions. So let's take H2m for the potential and Hm for the non-minimal coupling term. Then we can easily see this condition is satisfied and potential becomes flat at high field value limit. And as you can see, this m equals 2 with the gives you the quadratic potential and the quadratic non-minimal coupling term, and that is called Higgs inflation, suggested by Veshyukov and Shaposhnikov some years ago. Okay, and it is interesting to see this model in general predicts NS-R plane like here with different powers of the theory. So as you can see, the Higgs inflation with m equals 2 is in good agreement with the observations, with the R is around 10 to the minus 3 and NS is around 0.96. Okay, so this is the plot from the Planck collaboration. And indeed, you can see this R square inflation or Higgs inflation is giving you the best fit to the theory. Okay, and so R square and Higgs to the 4 with the minimal coupling is actually equivalent, mathematically equivalent. Okay, and this is simple and easy. So let me show you these steps. So let's begin with the Higgs inflation with the non-minimal coupling term and the potential. And during the inflation, especially during slow inflation, the kinetic term doesn't do much, okay, unless we are considering K inflation. And then you can solve this equation taking the equation of motion, okay? Because you can get rid of the kinetic term, you can regard this phi as auxiliary field, and you can solve the auxiliary field taking the equation of motion. So solution of the equation of motion is this, or phi square is Cc r over lambda. Then just plugging in this solution to your original action, you can get this. Okay, so here you can see the Einstein term and R squared term from the phi to the 4, and the coefficient is determined by the non-minimal coupling and the self-coupling of the Higgs. Okay, so it's Cc square over 4 lambda R square is introduced in a Starominsky model, and to fit the data, lambda over Cc square or Cc square over lambda, this combination has to be pretty large, 10 to the 10. Okay, and that is hardly understood in the original setup, but from the Higgs inflation setup, you can easily understand why Cc square over lambda is that large. Okay. In general, you can play the FR theory as the non-minimally coupled scalar theory, as Masaide described yesterday. So whatever the theory is, FR, we can always find the equivalent scalar and gravity theory taking this trick. Okay, so trick is this. So you can replace this FR to the F of phi with this additional term. Okay, here first derivative of F is regarded as Lagrange multiplier. Then you can find the solution to this system is given by R is phi. And by plugging in this relation in here, you can recover the original action. Okay, so this is a well-known trick to find the scalar theory from FR theory. So as I mentioned in the earlier to answer Kyun's question, we can always find the scalar theory from R plus R square, the inflation. Okay, so here you may want to memorize the shape of the potential, and that is given by F prime times phi minus F, and the non-minimal coupling term that is given by F prime. Okay. As I also mentioned earlier, so this combination lambda over Cauchy square has to be this small to fit the Kobe normalization, okay, to guarantee the success of the Higgs inflation. But in the beginning, it was questioned because Cauchy was lambda was considered to be order 1 in the original setup. However, we really have to take the RG running effect of lambda, the self-coupling, because of those 3 diagrams and also many other diagrams at the 2-loop level, you can find the lambda actually runs with respect to the energy, and this is the beta function of the lambda. Okay, and as we all know, the second term dominates with the largest Yukawa coupling for the top quark. So the second term, because the negative sign from the spin degree of freedom of the top quark, we can always find the beta lambda is negative in the standard model running. Okay, so that means the Higgs self-coupling becomes weaker at higher energies. So taking this, the running of lambda is depicted here, and from the 1/8 at the electroweak scale, we can find the tiny small lambda at a larger scale. Okay, here I take the window of M top, taking the pole mass uncertainties from the LHC. And you can also notice the beta lambda becomes tiny small here at a larger scale. So we can see the so-called Higgs criticality at high scale. Lambda becomes tiny small. At the same time, lambda prime becomes tiny small. Okay, we can use this property to explain the Higgs inflation. So, as I mentioned, lambda at high scale is tiny small, much smaller than the value at the electroweak scale, and you can easily understand why lambda over Cauchy square is small. So, for instance, lambda is order Cauchy non-minimal coupling is order 1 or 10 or 100. You can easily understood this 10 to the minus 10, taking lambda value at the critical point, 10 to the minus 6 or 10 to the minus 8, okay, depending on your scenario. And I also noticed this running of lambda and the criticality is consistent with the recent top quark mass measurement at the CMS. And they measured the running top quark mass with respect to the energy, and they found this nice data points. And taking this data points, indeed, the running of the lambda is really approaching to the criticality position at high scale. Okay, very good. Because of the time limit, I think I want to skip this. But anyway, we can also explain the small lambda C squared considering the clockwork mechanism. This work was done with Chang, the previous speaker. Okay, so let's close look at the action once more. So this is the model, right? So we have a non-minimal coupling term here and R squared term. Then this theory can be regarded as R and H type theory, and this type of theory can be transformed to the equivalent theory with R, H, and S, right? S is the scalar, another scalar degree of freedom from R squared term. So this is more details. So we can start from non-minimal coupling term of the Higgs and R squared term, and using the trick of FR, you can set up the theory with the additional scalar degree of freedom here. Chi is introduced. Then this is the R prime term, this is the F term, and this is the R minus chi term. Okay, so you can find the theory has a new non-minimal coupling term like here. So the theory has the Cauchy H square and also chi with R, and the potential include the lambda h to the 4 and the chi square, okay, new scalar potential. And then we can recover the action in Einstein frame, taking the Weyl transformation. And here the conformal vector is now determined not only by the non-minimal coupling term, but also by the scalar degree of freedom associated with the R square. And it is often introduced as the new field S given by this combination. And this S is actually the physical canonical degree of freedom in Einstein frame, and that is called scalaron. Okay, so now taking this Weyl transformation, you can recover the theory in Einstein frame. So in Einstein frame, the gravity is canonical, and this the scalaron has the canonical kinetic term, and H has the kinetic term with suppressed by the omega to the -2 and the potential. Here, the potential include both H and S, okay? And this is the form of the potential in Einstein frame. So here, this term is coming from the original Higgs potential, and second term is from the combinations of Weyl transformation and also the trick I mentioned earlier, okay? So the theory is now this. So let's analyze the perturbative cutoff scale of this theory once more, okay? So let's expand the theory near 0 and 0, okay? So you can easily expand this theory, and you can find all these terms from h to the 4 and to the higher order terms, and you can read out the cutoff from these expansions, okay? This is the result, as I showed you earlier, okay? To be more precisely, you can read the shape of the cutoff from the term given like this: h to the 4 s times k plus j power. Then this is the cutoff, okay? And if you consider h to the 4 and s of k, then this is the cutoff, and so on and so forth. And you can conclude lambda is always given by order of m Planck square of Cauchy square, ms square times mp, okay? And this can be larger than the Planck if you take the ms, the scalar mass is smaller than m Planck over Cauchy, okay? So just like Higgs in the standard model, taking the scalaron into account, the cutoff scale of the theory becomes larger than Planck, and that is desired result we want to have, okay? So therefore, from now, we take Higgs R2 theory as the natural setup to UV complete the Higgs inflation. All right, so this is the model. So this model includes 3 parameters: m, the mass of the scalaron, Cauchy, the non-minimal coupling term, and lambda, self-coupling of the Higgs. And they can also run with respect to the energy. So scalar mass runs with this combination of the beta function. Here, alpha is given by alpha is nothing but the coefficient of R square term. Okay, so considering this, you can calculate the running of scalar mass and the non-minimal coupling term. And this is the beta function of the non-minimal coupling, and that is given by this. Okay. Please notice if when Cauchy is -1/6, this doesn't run. That corresponds to conformal limit. Higgs self-coupling include the standard model running plus the running from the non-minimal coupling term. So you can draw the running of lambda with respect to the energy, and this is the shape, the tendency of the running. Okay. Okay, so taking all these things into account, you can draw the shape of the potential. And it is interesting to see the shape actually include the valley structure. Actually, this is natural because this theory belongs to so-called alpha attractor kind of model. So with this particular choice of parameters, m is 4.2 times 10⁻⁵ m Planck, and QC is order 100, and lambda mean is 10 to the minus 6, then this is the shape. And you can see this potential actually includes two plateaus, a high plateau and low plateau. Okay, and high plateau is mostly responsible for the CMB perturbation, and the low plateau is responsible for more smaller scale physics like PBH production. Okay. Okay, now let me change my gear and to discuss PBH as dark matter. Recently, the PBH got more attention because the window is identified for PBH. And in this window of the PBH, near the 10 to the minus 15 solar mass, we can actually explain almost 100% of dark matter. Okay. So this window is particularly interesting. However, of course, there are other windows with the heavier mass, and they have different implications to gravitational wave detection and also macro searches. Okay, but in any case, we want to ask if the Higgs R2 inflation can provide any size of a PBH in this particular window. Okay, so to answer that question, we need to analyze the Higgs potential more carefully. Again, we want to consider the critical Higgs inflation because we want to consider the theory which is more consistent with the standard model predictions. Okay, so the shape of the potential can include two different possibilities depending on the value of non-minimum coupling actually. So with the order 10 or order 100 non-minimum coupling term, we can find that potential include the inflection point, okay, in the middle. During this inflection point, the perturbation, curvature perturbation of the theory becomes enhanced. And during this, the inflection point, you can set the position of the inflection point gives you the mass of the PBH, okay? And so taking everything into account, so position of the inflection point and the duration of the inflection point, and also to fit the NS and R from the CMB, we have a particular window for the PBH in this case. We can also think of a different possibility of tachyonic instability. Here, the QC value is a little bit smaller than order 10, say 5 or order 1. Okay, so in this case, interestingly, this potential include this kind of the unstable valley of the trajectory. Okay, during this unstable trajectory, we can find isocurvature perturbation becomes enhanced. And due to this enhancement, we can find PBH production, PBH and also gravitational wave production. Okay, so we can really have enhanced curvature perturbation at small scales. Okay, so let me look into more details of a near inflection point. So again, this is the shape of the potential. With this combination of the parameters, we have two plateaus, right? And this, we need to solve the field evolution, taking the equation of motion and the inflation rolls along the minimum throughout the inflation. Okay, so through the inflation follows the valley structure, then meet the inflection point. And during this inflection point, the inflation takes the ultra slow roll phase, and taking this order 10 ultra slow roll phase, we can find enough number of PBH is produced. And this is the epsilon parameter and eta parameter, and this is enhanced. And having this USR phase, we can have growing mode in the perturbation. And we can find the curvature perturbation had with this distinctive growth of P of R with respect to K. Okay, that depends on K to the 4. Okay, so having this enhancements, this large enhancement, we can really have production of PBH. So this is the result from this inflection point running, and indeed we find the production is highly enhanced within this window of mass of the PBH. So here we find that F, that is the proportion of the PBH over the dark matter, that can reach really up to 70% or even higher, okay, within this desired window. However, to fit this number, we find the NS and R are modified a little bit, and indeed, more specifically, NS is tilted down to a lower value from 0.96 to 0.95. So these are the predictions to fit those PBH. However, we already know this can move toward the larger value of NS when we take slightly large R cubed term. For instance, 10 to the minus 6 times R cubed term gives you a slight better fit to Planck data. Okay, and this is preliminary result for the stochastic gravitational wave background, and I will show you the detail in later after finishing up this project. And if this prediction is correct, then Lisa and other experiments will probe this window, and we will see if the Higgs inflation can be really probed by the gravitational wave in the future. Okay, let me move on to the tachyonic instability, and this diagram is brought by my student Dong-Hyun. I think he likes this story, the little engine that could. So indeed, as I showed you, the potential can have the slight the hill, and to inflation can actually, inflaton can up the hill, taking the dynamics of the inflation. Then this up the hill, we can have the instability due to the negative mass, tachyonic instability due to the negative mass. So we can really have enhanced perturbation. Okay. So this is the detail. So this is the perturbed action in second order. You can really derive this equation from the action I showed you. And you solve this equation taking various techniques using unit vectors and so on and so forth. This is just the analysis, dynamic analysis of the theory, two-field theory, taking the potential into account. Okay, this is well-known procedure, and we do this procedure following the well-known method. This is the perturbation equation, and we find this the mass, square mass of the isocurvature field can be negative in some parameter choices. Then this isocurvature perturbation can be enhanced. Okay. So this is the global picture of the potential, and as you can see in the beginning, wherever you put your field, because of the valley structure, you always find your field follows this trajectory first, then has a turn, then has a very interesting zigzag motion due to the shape of the potential. And because of this motion, we can enhance the isocurvature perturbation. Okay, here in particular, those plots are taking this non-minimal coupling. Non-minimal coupling is 3.2. Okay, so this value is important to really generate the large enough perturbation. So having this isocurvature perturbation, this is the result. Okay, so you can really see the enhancement in the isocurvature, curvature and isocurvature perturbations. Okay, and this is the result for the gravitational waves, for instance. Okay, details can depend on the what parameter you are taking, and this parameter choice is related to the standard model measurement at the colliders. Okay, and this is the preliminary result for gravitational waves. Okay, and again, this prediction depends on the parameter choice. Here, for this particular plots, we take this non-minimum coupling 3.298 and 10 to the minus 5 Planck for the scalar mass. Okay, so changing these parameters, we actually find different predictions. Okay, so once those future experiments can really measure the gravitational waves, we will be able to learn the parameter choice of the theories. That is exciting. Okay, so let me summarize my talk. Higgs R2 inflation, or equivalently Higgs scalar inflation, is unitary theory with a large cutoff. Provides a successful inflation around 0.96 and 10 to the minus 3 for the tensor to scalar ratio, depending on the parameter choice. The potential of the scalaron and Higgs allows inflection point or the valley plus hill structure for tachyonic instability. Those two possibilities open a very interesting enhancement in curvature and isocurvature perturbation. And they can lead to a sizable production of PBH and gravitational waves. Okay, so even we find the PBH can be the whole dark matter in the scenario, and gravitational detection in the future will pin down the parameter choice we really take. In that case, we can really compare the collider experiment and the astrophysical observations, and that would be our nice future. Thanks a lot. This is my talk. Thank you.
Thank you very much for your clear talk, Professor Song Jang-Park. It's open to question and comments. Shuntaro, go ahead.
Thank you very much for the nice talk. Actually, I want to understand more about the condition for second plateau for PBH. As you say, you have 3 parameters in the model. And for example, for the case of inflection point impression, maybe you need to tune the parameter, maybe around the 3 parameters. So I want to understand what is the concrete condition for that.
Okay, thank you very much. So as we all know, the plateau at high scale is determined by the theory itself, R-plot structure, right? Mm-hmm. And the appearance of the second plateau actually depends on the running of lambda. So when lambda becomes tiny, small, like 10 to the minus 6, we can realize this nice plateau in the middle, in between the high scale to the low scale, okay? So the position of this lambda, this inflection point depend on top quark mass and alpha S parameter and Higgs self-coupling within the standard model. Okay, so to realize this particular shape of the potential, we find that the combination is limited. Okay.
See. So you also mentioned that because of the choice of such parameter, the NS and R are a bit deviated. Then you need to introduce the cubic.
Yeah, because of this ultra slow roll period, we need to move the total number of e-folding in predicting NS and R. So that's the reason why we find NS value is slightly smaller. That is still within the 2 sigma, by the way. But however, as I mentioned, if we consider our cube term with the 10 to the minus 6 as a coefficient, can actually help the situation and go back to the original prediction for the NS near 0.96. Well, we do not have any prediction for the R-cube, unfortunately, right? But we have feeling that R-cube can help the situation. So that's the situation, yeah.
What about the tachyonic instability case? I know the orthogonal direction to the infraton is always heavy during inflation. So to get the tachyonic instability, maybe we need to change parameter or something, right?
Right. Yeah, that's right. So, but in our case, we want to change the non-minimal coupling term and also the running parameter of lambda. So we find that this relatively smaller non-minimal coupling with the 3.2, we find the enhancement can be sizable, very sizable, and even produce PBH. Okay, so if this QC value becomes larger, we don't really think the sizable PBH can be produced, even though that can help to reheat the universe.
I think in that case, the tachyonic instability before the end of inflation disappear.
Yeah, these are completely, or I would say less significant.
Thank you.
Thank you.
Thank you very much. Any other questions or comments?
Can you show me the plot for primordial black hole masses predicted in your model as a function of the spectral index?
Okay. Yeah, actually, we have two different predictions. So one for the inflection point. This is from the inflection point, and the other from tachyonic instability. For tachyonic instability, we didn't generate the PBH plot yet. Okay, so this is the
for this
result for near
but
inflection
here
point.
Maybe you're focusing on the parameter space where the primordial black hole can be dark matter and stable dark matter.
Yeah, that's right. Yeah.
So if you go further to lower primordial black hole masses, you might be in the region where the primordial black hole becomes evaporating.
That's right.
And you have some constraint. So then, can you say more about? Let's say without R-cube term, we want to be more compatible with the CMB measurement in the spectral index, and then from this plot that the primordial black hole mass becomes smaller as you go into the Planck favored region, right? So then instead, can we put some bound from, can you put some bound on the primordial black hole in this case? Like, you know that if a primordial black hole becomes dominant and decays during the BBN, there might be significant,
yeah, I guess there are many ways to constrain this theory. As you mentioned, when the PBH mass becomes lighter, it decays faster and produces more energetic particles. Indeed, near here, near the endpoint of this region, you can really find the sizable production of the photon and also neutrinos and also axions, for instance. In that case, we can learn about the PBH, the Hawking radiation of the PBH, taking the gamma ray searches and also neutrino searches by Juno, for instance. Indeed, Juno people generate a paper constraining PBH decay to the neutrinos. Yeah, so actually, we are working on to see how this constraint can constrain the model of the Higgs R2.
Because I think the order one fraction is not allowed in this small mass window. And then the peak, I mean, the height of this this monochromatic peak depends on the perturbation, right?
Yeah, that's right.
Size of the perturbation.
Yeah, the height, how many PBH is depending on how large the duration of the USR. However, we do not want to enlarge the USR too much because it will spoil the NSNR.
Right. So because you have some freedom to reduce the amount of perturbation for small primordial black hole masses, then you can take it bound on your model probably. So just
yeah, I guess so. Yeah,
it would
right.
be interesting to think about it.
Yeah.
And also for isocoverture perturbation, you are working on this currently, but you are focusing on small scales to produce primordial black holes or something like that. So right. Does it also change or affect the perturbation at large scales, like in the CMB?
It doesn't seem so, fortunately.
It's a separate.
This kind of interesting dynamics doesn't include large USR region of the parameter. So it doesn't really change much about the NSNR. In that sense, this is nicer way of producing PBH. And
because the tachyonic instability is developed in a particular time window, right? Particular during inflation. So if I don't know if it happens too early, you might have correction.
Yeah, but the shape of the potential is given by the theory, and it doesn't seem to have more freedom to change much about the timing.
Or I mean, you are allowed to shift. I mean, this zigzag. I mean, this unstable point. You are allowed to change that time. I mean, time of instability. I mean, you have a freedom to change it, or I don't know.
Yeah. So first of all, in the earlier part of the evolution, there is a kind of valley. So wherever you put your inflaton in the beginning, you end up with always same trajectory, like here, and then this zigzag motion is already determined by shape of the potential. So we don't seem to have much freedom to change much. But we work now. So I will tell you later more details.
Are there any quick questions or comments? If no, let's thank Professor Chang Park again.
Thanks a lot. Thank you very much.